All right, so thank you for the introduction. And I will talk about, we'll go back to the basics, let's say, and talk about plasmonics with gold nanoparticle, and why gold, what are the role of the free electrons in gold? Are they always free? That's one of the questions. And so I am associate professor at Université Pierre et Marie Curie in Paris, part of the Institut des Nanosciences de Paris. And so I'm glad to be here to present this courses. It's not really the core of my research. I will say a little bit of my research. And first, what makes gold so special among other metals? And why is it so widely used for plasmonics? First, in the introduction, that's the outline of my talk, let's say. Gold is yellow, and it's yellow because of that direct equation, because of the relativistic effects which are in gold. I will discuss this a little bit. But it's not always yellow. Sometimes it's red. It's the same gold. And it's because of that equation, which is the polarizability of the sphere. And you see, that's gold also. And I will talk about this, all right? And is gold always conductive? You know, gold is used for a very good conductor, but it's not always conductive, and that's the research I'm doing. So I will just talk a little bit of this, but not so much. I have done a similar conference in a different audience, and they didn't like my introduction, so I have another one. What's the relationship with gold? You know, the novel from John Rowling is completely invented. Harry Potter doesn't exist. Hogwarts School doesn't exist. But maybe you have read it. I read the first books. And walking in Paris, I came to that street, Rue Nicolas Flamel. And you know, Nicolas Flamel is one of the characters in Harry Potter. That's the only one who really existed. That's the only real guy in Harry Potter novel. And so I was a bit surprised, so I tried to know a bit more about that guy. That guy was living in the 14th century in Paris, and he was like a librarian in the Sorbonne University, so had access to all the different books. And at the time when there was no library, no printers, let's say, and he became very wealthy. We don't really know why. And people say that because he had discovered the Philosopher's Stone. And so that's something. And I continue my work, and I find this Auberge Nicolas Flamel. So that's the most ancient house in Paris. Nicolas Flamel again. So he's here. And he was believed to be famous because of that Philosopher's Stone. And that's my point. You know, the Philosopher's Stone is the stone which was thought to be able to transform lead into gold. And what is interesting is the color of that Philosopher's Stone. It's red. It's red like gold nanoparticles. The same red. And actually, what happens, at that time there were a lot of research towards gold, and they succeeded probably to do some gold nanoparticle. And with this, they had made halfway to real gold. If maybe you don't really know about medieval philosophy, but I will just talk one word about that. Medieval philosophy was thinking that every being is made of matter and form. Let's say of matter and the soul. So for a living being, we can understand what is the soul. But for a stone has a soul for the medieval philosophers. And the soul of a stone is its color. So if you can get the color of a stone and put it in another material, you can transform lead into gold. And so that red color was the soul of gold. So Nicolas Flamel probably succeeded, and it's known that in the medieval time, they were doing some red gold. So they had already captured the soul of gold, and they wanted to put it to lead. You know that it didn't work. And so the story stopped there. But they were already gold nanoparticles. And so that's the second outline of my talk. I will talk a little bit about why is gold yellow, and then why is nanogold red, and this is plasmonic. So why is gold yellow when all the different metals are gray, except when they are oxidized? There is only copper and gold, which are not yellow. And this is, if you plot the absorbance as a function of wavelength of gold, you see that it's absorbing in a blue, so in high energy region. So it's absorbing high energy photons. And so as a result, there is just the remaining color, which are yellow, orange, and red. So that's the color of gold. It's not an explanation, it's just a measurement. And explanation comes from what are the electrons who are playing a role in the color of gold. For this, so we go a bit more into the details. It's due to the relativistic electrons that are around the gold atom. So the simple image is that just an atom is made of a core with an electron, so surrounding that core. And if it's a simple picture, we know that with quantum chemistry it's not exactly like that, and so on. And but if you consider that there is, because of the speed, there is a relativistic effect, which will lead to a contraction, apparent contraction of the radius of that electron. And that contraction, so that the 6s electron of gold can be evaluated to be, so the speed is 0.6 the speed of light, and the contraction is not negligible at all. And so as a result, the 6s orbital of gold will shrink. And since there is another, so the d electron, there will be more important relatively than the free electrons. That's the reason why gold, as in gold, the d electron, so the core electron, are playing a more important role than in silver or in the platinum, for example. If you compare the different elements of the periodic table, so this is a work made by Pekka Pico published in 2004, so when a work done much before. You can see this very interesting view graph. In the axis you have the Z number, so platinum is here and that's the contraction of that orbital. And you see that gold is very, very special, because with the number 79, which is gold, you have really a dip. So that's the contraction, so that's the radius, the relative radius is really contracting. And it's not the case for the other metal. And this has, so that's the guy who worked a lot on this. This has very strong consequences on the optical properties of gold. Optical properties, that mean to the electrons, so you know very briefly, in case of an insulator, the Fermi level, and the valence band and the conjugate bond is a huge gap, so the electron with energy coming from the light cannot go to the conduction band. Semiconductor, it's easier. In kind of metal, the Fermi level is inside the conduction band, so if you have energy coming from light, it can easily promote an electron to the conduction band and make absorption. If you go into a more complex structure like gold, the conduction band, I mean the Fermi level is into the conduction band, and that conduction band is made of so the p and s electron. And with this, you will have two kinds of transition. If you have low energy electron coming from light, you will have intraband transitions. And intraband transitions are very easily described with the Drude model, so for free electrons. And if you want to capture the behavior of light into a material, you will use the index here. Index is the dielectric function is the square of the index. They are complex number. If you just consider metal like silver, where the bound electrons are not playing a large role, you will have something like a decreasing shape like this, and so that's the kind of hyperbolic shape. But if you look, so that's the dielectric function as a function of the photon energy. If you look at gold, that's very different. This is I mixed up the two, that's the epsilon prime, so this is the absorption of light captured in the dielectric function. With silver, there is no absorption until 3.5 electron volt. That means in the visible, silver is not really absorbing. That's the reason why it's reflecting all the light. It's gray. With gold, so that line, you see that there is this beginning with the hyperbolic shape, and then there is a strong absorption due to this d electron. So that's the interband transition. So electron promoted from the valence band to the conduction band. And this is due to that relative importance of the d electron. And so you see with this measurement that the two metals, silver and gold, are very different, and copper is also quite similar to gold in terms of interband transition. Just selected property, the interband threshold, so the minimum energy that electron must have to promote this d electron to the conduction band for three metals. For silver, the threshold is 3.9 electron volts, which is in wavelength 320 nanometer. It's in UV, so it's great. Look at gold now. That's 1.82 electron volts, so it's now in the visible. So it's absorbing in the visible. So that's the reason why it's yellow. And copper is even it's at 590 nanometer. So with this, we can understand why gold is a bit special in terms of color, yellow color. But now, what's happening when you shrink one of the dimensions of the gold? I was talking about bulk gold. With this, you can shrink either one dimension or the three dimension. And it gives birth to the two plasmonics effect, to the two plasmon, one which is, and that's the surface plasmon, and the other one which is the localized plasmon. Surface plasmon, so we shrink just the dimension in one dimension, we have a surface wave, and the localized plasmon, it goes into nanoparticles. I'll speak about the first one first. So, this surface plasmon wave, so we go a bit into the electromagnetic. Imagine an interface between a metal and a dielectric. And if you want to know what kind of wave we have here, imagine just a plain wave with a wave vector k. Wave vector k in the metal will write k1x, so along the surface, plus k1z, perpendicular to the surface. Imagine, you will know how we do it, that this wave vector is imaginary, is a complex number. The 1x is real and the other one is imaginary. If you put that back into that equation, what you have, it's an evanescent wave, surface wave. It's really easy because that's the I will cancel and give a minus with that one, and as a result you have an exponential decay term here, which is along the z direction, and so that means that the amplitude of the wave will decrease as long as you go deeper and deeper in the interface, but you still have a kx, which is propagating term, and which will describe the wave crawling along the surface. This is a surface wave, and that's the surface plasmon wave, which is so interesting for many applications. The question is how to promote such a wave, how to make it. If you just shine a laser on the surface, it won't work. You won't make a surface wave. And this is ruled by the dispersion relationship, which is a relation between the k and omega. energy of the wave and the direction of the wave, let's say. And if you look at what happens in gold, you will have typically a decay term in deepness of 30 nanometer, so penetration depth is 30 nanometer, and it's still absorbing in the plane direction about microns, between 1 and 10 microns. So it's a wave which will crawl along the surface of 10 micron and very thin 30 nanometer. So first is what is surface wave? The second, how to excite that surface wave. So we have to ask that to the dispersion relationship. Dispersion curve, actually it's just a plot of the two main conservation laws in physics, conservation of energy, conservation of momentum. And so energy is h bar omega over c, and the wave vector is h bar k. If you plot the dispersion curve of just a normal propagating wave in vacuum, you have something like omega at kxc, very easy. So it's a line. So if you plot omega as a function of k, that's the green line. And now you ask, I want to plot the dispersion curve of a surface wave, the one I described before. What you got is that relationships omega at kxc over a square root of a relationship with epsilon 1, which is the dielectric, and epsilon 2, which is the metal. And epsilon 2 is the gold dielectric function. So that's something you can measure. You put that into that equation, you plot it, and you have that curve. The problem of that curve is that it never crosses the green lines. So there is no point where you can have conservation of energy at momentum at the same time. So with just a line shining laser of a gold surface, you don't have evanescent wave. You have to find a trick to do that. The trick is the following, is to use a prism, that's the Otto Kretschmann configuration for Plasmonics. This one is Kretschmann. And the trick is just to arrive with, not from the air, but from medium with a higher index. In that case, if you look in glass, what's the dispersion curve is the same as in air, but over n sinus theta. N is greater than 1. Sinus theta, if you don't go to normal, it won't be so high. So that number will be greater than 1. So the slope will decrease. And decrease so that it will go to the blue line, and it will cross that dispersion curve. And at that point, you will have excitation with that light coming through the prism of the surface wave. That's the trick, to have to generate this surface wave on gold. And that's the reason why it has been discovered, a century ago, theoretically. It has been observed with just electron bombardments or another condition. But optics, the observation of this is 1972, 1975, with Kretschmann and Andreas Otto, who came here last year. And what is really interesting in that kind of wave is that it's very, very surface sensitive, intrinsically surface sensitive. How to detect that? I will illustrate this with a very simple setup I've been using so for my teaching. So it's lab experiments. You can do it with this very simple setup with just a laser, polarized in the p direction. I didn't talk about polarization, but the wave should be p polarized to excite that dispersion curve I show. And it will reflect on the prism. And then this surface wave, you cannot detect it directly, because it will mean that you need to put a detector in a 30 nanometer thick layer, 1 micron. It's not possible, except using near field scanning optical microscope, but for lab work, for students, not possible. What you are doing is just reflect what is reflected by the surface, what remains. If there is an interaction, the energy of the laser will be absorbed. So there is a dip, and as a function of the angle, I draw that absorption, and this is the Plasmonics section, where the external light is coupling to the plasmon wave. So there is less reflected light. And what you could see, so that's still the setup. I will go fast on that. If you change the color, for example, change the wavelength, you will probe different part of the dielectric permittivity of gold, and you see that the shape is changing. That's with helium neon laser, 633 nanometer, you have that kind of shape. If you go more into the high energy, low wavelength, you will go into the infrared transition. There will be losses, and these losses will go into the resonance is less and less pronounced. That's the reason why when you really want to have a sharp plasmon excitation, go into the infrared, and you are more sensitive. I'm using this experiment for kids. Don't say anything about electromagnetic waves, but just say that by shrinking one dimension, gold is reflecting different colors, and because it will absorb different wavelengths. When you have at a given angle, it's yellow, and when you change the angle, so you change turn the prism, it will absorb different wavelengths, and the color will be changed. So that's a proof that there is really a wave created in. If you just blow on the prism, the color changes automatically, demonstrating the great sensibility of this kind of plasmonic wave. In real life, in research life, what is it used for? Two applications that I will just very briefly. The most wide one is surface plasmon resonance biosensor. In that case, what you want to do is to put a cell, chemical cell, against the gold surface. And you will add some different chemical. You need first to prepare the receptor. So the idea is to functionalize the gold surface with a receptor able to capture, for example, immunoglobulin, which will recognize the antibody, another protein. And if you look at different sequences, this is the absorption, the extinction curve, as a function of how much milligram per milliliter you add in the solution. 1 milligram per milliliter, 2 milligram, and so on. And if you measure at one given wavelength and inject the solution in the prism, the cell, you will see some decrease. And by studying the speed of this evolution, you can get, if the information, whether the antibody has recognized the protein or not, and whether there is a real recognition. And this is really widely used in biochemistry, this kind of SPR apparatus. Of course, the one I've shown before, it's for lab experiments. It costs something like 4,000 euro if you buy it by a small company. This kind of special setup costs more than 40,000 to 50,000 euro if you want to really do some precise and accurate measurements. What happens now? So that's the propagating plasmonics. What happens now if you shrink not only one direction, but the three of them? You get nanoparticles. Nanoparticles, that's one step into, let's say, the nano world. This was, just to give an idea, it's interesting to have numbers like that. If you are going into a plane, you see, you could see maybe a road over there. And on that road, imagine there is a hair, and you want to study the hair with from your plane. That's what you are doing with the AFM, STM, studying atoms. And so this is the kind of thing you do. You are doing this with your AFM, STM, and just looking at this panorama, you can imagine, if I'm lucky, I get the hair on the road. But maybe, if I'm not lucky, I will go into the mountains and say something completely different. And that's the reason why you need something very well reproducible so that what you study in one, so let's say, 500 nanometer by 500 nanometer can be applied to the whole, what you see, the whole panorama. So different steps, I will, you know them. These are this kind of nanoparticle seen from my plane. So from my chair, looking at my AFM window. So 50 nanometer nanoparticles on deposited on the surface. How could you prepare gold nanoparticle? The first scientifically prepared nanoparticle, they were done by Michael Faraday in 1857. And so with my colleague Catherine Louis, we made again the experiment. So just if you appear here. And so you start with chloric oral acid, and you add citrate. Citrate will have, so gold is at the oxidation state 3+ here. You need to reduce gold so that you have metallic gold, and metallic gold nanoparticle, is reduced by citrate to metallic, and if you do just reduction, what you will have is precipitate. So what you need to do at the same time is to cover gold so that you will block the aggregation. This is done always also by citrate in that case. That's the most simple way to make nanoparticles. And so it has two roles. It will block the size of the nanoparticle and at the same time reduce it. If you change the ratio gold nanoparticle, you will be able to change the size of the nanoparticle. The more citrate you add, the more coverage you will have, so the smaller the nanoparticle will be. With this kind of method, you can have nanoparticle functionalized with citrate from, let's say, 10, 15 nanometer up to 80 nanometer. So there are hundreds of the different methods. I'm sure we will discover some new one during that conference here. If you have just spherical nanoparticle, they are ruby red, as it says, and that's nanorods. If you change the shape, you will be able to change the color along all these different colors. These are all gold nanoparticles. So, as I said, they have been used for years for decoration. There was a special manufacturer in France, in Orléans, which was specialized in doing some glassware like that with gold nanoparticle in the 18th century. The story is quite funny because it was then, it went into, that was that one. So it was used for decoration of pot like that. And very recently I met a colleague, a chemical colleague from New Zealand, who is trying to do some scarf with gold nanoparticle, trying to sell them. And so I don't know the story, if it's going to be a success story or not. But he's a chemist and his father owns ships. And so he meets both of them. And so that's quite nice. I don't have samples, sorry. How much? 10 minutes or? 15 minutes. So let's go back into science. Into that, so that's the second plasmon, the LSPR, localized surface plasmon resonance, which is an electromagnetic wave which is confined into a very small particle. In that case, you will have, if you draw the absorption as a function of the wavelength, there is a resonance, very pronounced resonance, which is the resonance that gives birth to that color, the ruby red color. If you want to predict the plasmon theoretically, you can go to that article in 1908, spend 2 or 3 weeks scratching your head, and it's wonderful. But so he has modeled the diffraction of a wave into very small particle and expanding it into multiple expansion, let's say. But if you are dealing just with simple case, you can stay with the electrostatic approximation. It's it's homework that we are giving to our master students, so they don't like it especially, but I can go until the end of that homework. In that case, I'm go very very quickly into the math of that electrostatic approximation. Imagine so there is an electromagnetic field which, with the wavelength is much larger than the radius of the particle. So as a result, that particle will feel kind of homogeneous field. There is no change between the field on the right of the particle and the left of the particle. So as a result, you will polarize the particle with charges which are going to oscillate as a whole in the particle. This, you can model it with this polarizability and get to alpha, which is the polarizability of a single sphere. This is a bit tricky because here you need to use the boundary condition in spherical coordinates and use Laplace, so that's the mathematical part of it. But when you have done this math, that 2 or 3 pages, you go to that equation and you are done with this. And this really expresses the electromagnetical confinement, because sometimes we're just wondering, why is the nano world so different from the macro world? So there are many reasons, but one of these is the confinement in very small dimensions. And here the confinement goes through the boundary conditions and so on, and that explains that the polarizability of a sphere is completely different of the polarizability of a bulk metal. And then you just need to draw, to plot this polarizability. So you can go to the absorption cross-section, which is something more macroscopic. And so macroscopic that you can just make a measurement, use gold nanoparticle in water, in a small cuvette, you put that in a UV visible spectrometer. You have the blue curve with a plasmon peak at 520 nanometer, which is green. And if you plot, and I will need my battery, I think, if you plot the polarizability as a function of the wavelength, you have almost a match between the two curves. Almost, of course. And when you want to go more into... Thanks. Of course, if you want to go more into detail, why the width is not the same, and so on, why is the height exactly not the same, you are going into not the trouble, but the interesting physics, let's say, the Mie theory and so on. But for my purpose, it's not necessary, because you can have a lot of interesting information with this. This is the permittivity, dielectric permittivity of gold. Okay, so if this is the dielectric permittivity of the surrounding medium, if you change the medium, you will change that shape. You will change as well the position of the plasmon resonance, and so. Yeah, that's something that we will play with. This model, simple model, works in specific conditions with spherical particle, with not too small, not too large particle, so between let's say 7, 10, and 50 nanometer, and when the distance between two absorbing medium, 2 nanoparticles, are greater than 1 radius of particle. And when you get closer, there is strong coupling, it doesn't work anymore, and so this is against serious physics, let's say. Why is it gold? Sorry, there is a little bit French left here. So different from other metals for plasmonics. If you want, from that equation, if you want to predict what is the maximum of that resonance, you can, so it's quite easy, come up to that equation. Omega, so the resonance plasmons resonance occur at omega p, so that's a bulk plasma oscillation over a square root. If you just have m is the surrounding medium, if you have r, it's going to be 1, and So if now with gold, what happens if you do just this, you will have that. The plasmon resonance will be 5.2 eV, which is not visible at all. So that means that there is something missing in that formula. What is missing is the interband transition I was talking about at the beginning of my talk. If you add this in that formula, you will end up with 2.5 eV, which is the green again. So with this formula, you can, adding the interband transition, have a good idea of what will be the resonance of gold nanoparticle. But as I said, the particles are absorbing in the green. So as a result, what you get when you look through that solution is all but green, which is a complementary color of green, which is red. That's the reason why the gold nanoparticles are red. But when you do some biochemistry, functionalization, and so on, you want sometimes to change the color. What are the tools to change the color? Not the size for gold nanoparticle. Not the size, except if you go in second order phenomena. But if you stay in, let's normal size, between 10 and 100 nanometer, the size will not affect a lot. But what changes a lot is the surrounding medium. For example, here, that's the gold nanoparticle in air. You have a maximum in 505 nanometer. You put that particle in water. So that curve here, the plasmon shift to 520. You put them now in silica, so in glass, and the plasmon goes to 550. And then if you put them into very high index material, like TiO2, the plasmon goes to 700 nanometer. So it will change a lot, but of course, if you have your particle already in silica, you cannot change the surrounding medium with just, it's done. So another tool to change the shape is the nanoparticle resonance is the shape. If you go from a sphere to a spheroid, like that, so you just squeeze the sphere, you will have, so in that case, we have just a squeeze of factor of 2, one side of the sphere, and in that case, you will have two resonances, one which is longitudinal and the other one which is transverse. So it will split into two resonances, one which will be, in that case, in 540, and the other one will be shift downwards a little bit from 505 to 500, so very little. In that case, you can calculate it completely. If you go to more complex geometry, and the kind of electrostatic model on the Me theory cannot account for complex geometry, so you need to go into DDA calculations. And for example, that's an example of somebody who, Mrs. Noguez, who made in 2007 the calculation for different shapes. Sphere, you just have one resonance. Go to icosahedra, you will have something with multiple resonance, but due to the width, you have just one. If you go to the cube, for example, it's a more complex one because you have many multipolar resonances. And so when you have actual nanoparticles, they are in between a sphere and a cube. And very often you don't have just one resonances, but several shoulder due to the different edges that are in the nanoparticles. And the last way of changing nanoparticle is use core shell nanoparticle. I won't discuss this, but you just have gold nanoparticle into, for example, silica shell, and that's the most, or the reverse, silica core with gold shell around. This is the most used by biochemists who want to have gold outside so that they can do the chemistry on gold. There is a lot of biochemistry possible on gold, and to shift the plasmon to the desired wavelength. A short few words about supported gold nanoparticle. Sometimes, I mean, for my research, I never used nanoparticle suspended in liquid, but I want them to lie on surfaces, conductive, insulating surfaces, and so on. And so I just start with a gold nanoparticle in solution, and by silanization of silicon surface, I can deposit gold nanoparticle. I go on that, but in that case, you will have different effects. If you imagine a gold nanoparticle on a metallic substrate, the fact that there is a polarization, so plus and minus, on top of a metallic sphere, if you have minus, you will have a charge image below, the plus, which will appear. And so that means that when you have an oscillating dipole on top of the surface, there is another one oscillating beneath the surface, the image dipole. The two dipoles, if they are too close to each other, closer than one radius, they will interact. And by interaction, they will shift the wavelength. And so that's what has been modeled by here. In the two cases, when the excitation field is perpendicular to the surface, in that case, if the particle is very far away from the surface, 100 nanometer for 80 nanometer particle, there is no interaction. If you make it closer and closer, it will start to interact, and you have, when there are 0.01 nanometers, or very close, you have something which is completely shifted. And similar effect if you use electric field which is not perpendicular but parallel to the surface. So this is another effect when you have well-shaped nanoparticle with the given wavelength, and you put on the surface, you may expect some changes. In case of very small particle, smaller than 4 nanometer, the plasmon vanishes. I won't discuss this neither, but for those who are doing catalysis, they would like. So you know that only very small nanoparticles, smaller than 4 nanometer, are active in catalysis. But at the same time, you cannot see them with plasmonic anymore. And so that's a pity, but it's good to know. And finally, if you took 2 nanoparticles, put them closer and closer, so people have really measured that, Naomi Alas in Texas, and so demonstrate that there is really an interaction. I won't discuss this. Finally, what happens when you look at the field just outside the nanoparticle when you shine a light on a nanoparticle? There is a very interesting effect which is a field enhancement. That means that around that nanoparticle, you can calculate with the electrostatic model how much the field is modified. And what is very interesting, if you put number here, you find that it's multiplied by a factor of 5. So intensity multiplied by a factor of 25, something like that. So you have a very local field enhancement of few nanoparticle radius of extension, which is extremely used to have this kind of very good sensitivity. More or less the same process as we have in propagating plasmon, but here it's around a nanoparticle. And it's really widely used for cancer therapy. And that's almost the end of my talk. So just a very inspiring experiment, which is found experiment already 10 years old, where Sokolov in Texas used gold nanoparticle to target special cancer cells. Cancer cells, some of them are overexpressing some protein, so EGFR in that case. So what he does is to equip the gold nanoparticle with anti-EGFR. That means that if that particle will meet cancer cell, it will stick to it. And if this occurs, there will be a plasmon shift because the surrounding is modified, as I described before, of something like not much, 6 nanometer, but enough to measure it. And what he sees in his microscope, you have here optical microscope with 4 cells. One is a healthy cell, and 3 of them are cancer cells. These cancer cells have been surrounded by gold nanoparticles because this overexpressed protein has been targeted by the gold nanoparticle. And what it does is just use the laser, heat up the nanoparticle, and you know, if you heat up the cell for a few degrees, it dies. And so with this, it can destroy selectively the cancer cell. So it's going to be used in mice, and that's something that is currently in clinics trials now. And the last part I won't talk about, because Louis Caillard, who is here, will talk a little bit tomorrow about how very small nanoparticles can be made, let's say, insulating. So that's another topic. And I will stop here with, after having described these two plasmons, which is very important, is to really make the difference between, because in the literature there is kind of mixture between these, the propagating plasmon and the localized surface plasmon. Localized plasmon is not surface, it's volumic, but it's called now LSPR. But there are two different guys with two different physics behind, and so which are really widely used this last year. And I thank you for your attention.
Thank you, Dr. Pluchery, for your exciting lecture, very interesting lecture. And a couple of questions, if someone.
So I'm interested for the your business with this substrate, when you say that you can immerse into the gold precursor and obtain on the surface some particles. How you avoid the aggregation of these particles, and did you saw any like self-assembling of the particles on the surface?
Yeah. No, I didn't. Actually, there is aggregation, that's sure. I cannot avoid it completely, and if you see here, there is. So these are AFM picture of 50 nanometer. So due to the convolution of the tip, if the particle are 50 nanometer, the tip will show it as 100 nanometer or 60, 100 nanometer. So these ones are not touching. These ones are not all touching, but some of them are. And in that case, it will show up as an aggregation. There is a very small shoulder here. And for this, I'm not really, since in the optical visible spectra it doesn't really affect, I'm not really struggling against this. What I'm doing before is usually to sonicate the gold nanoparticle colloid so that it will disaggregate the aggregates that may be in solution. But after that, when depositing it on saline surface, the enemy number one is silane itself. So if there is still silane physisorb on the surface, when you put that into the beaker with gold nanoparticle, they immediately turn to blue. So it's finished. So in that, that's very special experiment. So I cannot avoid completely aggregation. I can just minimize it, and I'm not trying to do self-organization with this kind of substrate. I'm just using the plasmonic effect of, let's say, isolated nanoparticles.
Okay, thank you. Is someone question? Okay.
Excuse me, if there are no questions anymore, I would like to make a short comment, if possible. Okay?
Very short.
A very short comment. So last year I presented a lecture about infrared spectroscopy of functionalized gold nanoparticles, which is why I'm interested in this topic. So you can see part of it in my chapter. So my comment is that you said that for plasmonics, the size of gold nanoparticles maybe are not that important because the plasmon then does not shift that much if you change the size from a few nanometers to up to 100. But what really matters is the size. When the size of the gold nanoparticles really matters is when you functionalize your gold nanoparticles, especially with large protein molecules. In this case, for small nanoparticles, which have already their plasmonic resonance peak, they do not, they can be functionalized, but they do not change much the secondary structure of the protein because they are too small. If you take a larger particle, the proteins have more binding sites. In this case, their secondary structure is changed, and it has sometimes it has a dramatic influence on the properties of functionalized nanoparticles. This should be taken into consideration when you develop some applications. Thank you very much.
No question. Thank you again.